Okay, this is Physics 140, the best way to begin your day. And today we are solving problem number 698, a problem on finding rock. An object has several forces acting on it. One of these forces is F, a force in the x direction. This I hat indicates that the force is in the x direction, whose magnitude depends on the position of the object. It depends on x and y. It depends on the coordinates of the object, and is just a constant. So we asked to find the work done on the object by this force for the following displacements of the object. The object starts at the point 0, 3 and moves parallel to the x-axis to the point 2, 3. The object starts at the point 2, 0 and moves in the y direction to the point 2, 3. And the third case, the object starts at the origin and moves on the line y equals 1/2x to the point 2, 3. Okay, so let's begin by drawing these three paths. Let's begin by drawing these three paths and while trying to find the work. Okay, so in this case, well, we are given force, right? So force is alpha or A, x, y, I hat, where alpha is a constant, 2.5 newtons per meter squared. Okay. Alright, so we are given three paths, so that's our xy plane, and we are given one path, 0, 1, 2, 3, 1, 2. So our first path in part A is this, okay? Our second path in part B is that, and the third path in part C is this, right? We are going along the diagonal of that square, and well, for three different parts, we are asked to find what is the work done by this force. Okay. All right. So notice that for one of these three paths, we can find the result of the work of this force pretty simply. Notice that in case B, over each short time interval, the displacements are always perpendicular to the force, right? The force is always pointing along the x direction. Notice this I hat, and the displacements are always along the y direction, or each short displacement is along the y direction. So the dot product of these two is simply 0. So in part B, we can simply say, well, since force is along the x direction and the displacements, short displacements are along the y direction, the dot product of the two, F dot ds, is always 0. Okay, so work in this case is simply 0. If you add as many zeros as you like, you still get a 0. Okay. Now, the situation is more interesting for trajectories A and C. First of all, notice that we cannot use the definition F dot displacement in this case. Why? Well, the answer is simple. We cannot use this definition because force is not constant along this trajectory, right? So force is not the same here, 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 or here. So, well, which value of the force do we use? Okay? So we cannot use that. We have to recourse to the more general definition. We have to use the more general definition with the integral, while integrating the contributions of the force over each short displacement. Okay, in case A, let's consider case A first. Well, in case A, each displacement is parallel to the x-axis, right? So we can write this short displacement ds, the vector of short displacement dx, as simply, well, its magnitude, which I'm going to call dx, times I hat. It's along the x-axis, right? That's my ds vector. So, well, I can write so my force is along the x-axis and my displacement along the x-axis. So, well, I can write the dot product of the two for each short displacement. Well, each has only x component, so it's x component of the first vector times the x component of the second vector, and there are no y or z components. So it's simply, well, the x component of the force, alpha xy, times the x component of the displacement, which is dx. Right? That's my dot product. So my work as a result of that, is the integral of f dot ds. Okay. So it's the integral from the initial to final point of alpha xy dx. Alright, so how do we compute this integral? Well, notice that alpha in this case, well, alpha is a constant, right? By definition, alpha is a constant, so alpha is just simply 2.5. And in this case, in the case of trajectory A, y is simply a constant as well, right? So y stays the same throughout this trajectory, y equals to 3 everywhere throughout this trajectory, so, well, y is a constant as well. So I can put both alpha and y outside the integral. So what's left is the integral x dx taken between the initial value of x, which is 0, initial value is 0, and the final value of x, which is 2, so from 0 to 2. Okay, well, we know how to compute this integral, so it's alpha y, so integral x dx is x squared over 2 taken between x equals 0 and x equals 2. Alpha is 2.5, y is 3 throughout this problem, throughout this trajectory, so it's 3, and x is, at the upper limit, it's 2 squared over 2, and at the lower limit it's 0, so we don't have to take it into account. Well, during the arithmetic, it works out to 15 joules. 15 joules. Alright, so what do we do in case B? How the case B is different? Well, the case, not B, the case C. How is case C different? Well, case C is different because we have a different trajectory. Okay, so now displacement is not along any particular axis. It has both x and y components, right? So it has some component along the x-axis, and it also has some component along the y-axis. So overall, we can write this vector ds as dx times I hat plus dy times j hat. So we have both components. Alright, so now let's find the dot product. Well, force is still, however, along the x-axis. So when we do the dot product f dot ds, well, we need to take the x component of the force multiplied by x component of the displacement, y component of the force multiplied by y component of the displacement, plus z component of the force and multiplied by z component of the displacement. Well, luckily, in this situation, we have only x component of the force, so we don't have any yz components, so the last two terms are simply 0. Okay? So my result is fx alpha xy times dx, the x component of the displacement. So the result of this dot product is the same as in the previous case. For case C, case A, the dot product is the same. Now the value of the integral, I just took a clean piece of paper. So the value of the integral, how do we find the value of that integral? Well, in this case, work is again dot product of force and displacement. So it's still the integral from the initial point to the final point of what we found. The dot product of f ds is alpha xy dx. So again, these look the same. In the case A, in case C, these integrals look the same. Now, what do we do with these integrals is vastly different, however. Well, in the previous case, we could pull y out, well, because y used to be a constant. While in the second case, y is not a constant. Y varies with x according to, well, 1.5x. 1.5x. So in this situation, we have to take into account that y is a function of x. So we still can pull alpha out, well, but we have to replace y with its dependence on x, 1.5x dx. And we are still integrating over x from 0 to 2. 0 to 2. So the final value of the integral is going to be very different because now the integral is x squared dx, right? So it's alpha times 1.5 times integral x squared dx from 0 to 2. So, well, what is our result? The result is alpha times 1.5 times x cubed over 3 taken between x equals 0 and x equal 2. At the lower limit we still we again get the 0 value, and at the upper limit we get, well, 2 cube 8 times 1.5. okay, so it's 2.5 times 1.5 times 2 cube over 3, well, which works out in this case to 10 joules. 10 joules, the result, which is different compared to the result for part A. Alright, I think that completes the problem.